Okay, that's a tutorial on how to analyze a simple beam, and the best way to tackle this problem is just directly by going to the example I'm providing right here. So consider the beam shown in the figure, and we can see that beam in the figure right here. Part A says write the equations for shear and moment for the beam using an origin at end A. So we're gonna write the equations for the shear force and the bending moments, assuming that the origin is at point A. Then in B, we will be using these equations we developed in part A to evaluate the moment at section C, which is 5 feet away from the support at B. In part C, we will locate the point of zero shear between B and D. So if we are going to draw the bending moment and the shear diagram, we will definitely see that the shear diagram will cross the horizontal axis at some point between B and D. We need to locate exactly where it crosses that horizontal axis. Then we're going to use the equations to evaluate the maximum moment between points B and D. And finally, to wrap it up, we're going to draw the shear and bending moment diagrams. So let's get started. First of all, we need to calculate the reactions first of all. So that's my beam. And first of all, before doing any reactions, any distributed load should be a point load. So my first point to do is to introduce the reactions. At point B, I'm gonna have one vertical reaction going up called By, and at point D I'm gonna have another vertical reaction called Dy. Just remember this: whenever you assume a reaction, just assume it in any direction you want. There is no such thing as wrong or right, as long as the number of reactions is correct. For example, I'm assuming these to be pointing upwards. If my assumption is right, by the end of my calculation process, if the reaction forces, the magnitude is positive, that means my assumption or direction of assumption is correct. If they turns out to be negative, I simply assume the direction wrong, so I'm gonna flip them. Okay, so what do we do now with the distributed load? We concentrate it. How do we do this? We multiply the value of the load over by the length of distribution, which is 16. The value is 3, the length is 16. So simply 3 times 16 will give us 48. And we will concentrate at the middle or the midpoint of the distribution length, which is 8 feet away from point B, or from the support at B. So that's what we have so far. We're gonna go ahead now with the equilibrium equations. Now, how many equilibrium equations do we have? We have 3 of them. Summation of the forces in the x direction should equal to 0. The summation of the forces in the y direction should be equal to 0, and the summation of the moments about a point should equal to 0. But here's the thing: I don't see any force acting in the x direction, so I'm not gonna use the first equation, which is the summation of the forces in the x direction equals to 0. I'm gonna just leave this equation out of my way. I'm gonna jump ahead into the summation of the forces in the y direction equals to 0, and I'm gonna assume any force pointing upwards to be a positive and any force pointing downwards is gonna be negative. So what do we have? We have By plus Dy equals to whatever is pointing downwards. Usually we write it like this: By plus Dy, or some people will go ahead and start counting the forces from the left all the way to the right. They're gonna start something like minus 8 plus By minus 48 plus Dy equals to 0. It's just an old habit. I usually do the forces pointing upwards to be on the left and the forces pointing downwards to be on the right of the equation, and all of them will have positive sign. It's basically the same thing. So by plus dy should equal to the forces pointing downwards, and by moving them to the other side of the equation they're going to be positive now, which are 8 plus 48, and that's equation 1. Now I'm going to take the summation of the moments about point B, and I'm assuming the counterclockwise direction to be a positive. Okay, so we have dy, I'm rotating about point B, so dy multiplied by the 16, and it's rotating counterclockwise, which is positive, so it has a positive sign. Then the next force is going to be 48 multiplied by 8, and 48 multiplied by 8, it's going to rotate clockwise, which is negative to what I'm assuming, or opposing what I'm assuming, so it's going to have a negative sign. Finally, I'm going to have the 8 multiplied by the 4, and it's going to be rotating counterclockwise. Okay, one will ask, what about by? Remember, we are rotating about point B, so any force passes through point B should not be counted into the summation of the moments, because basically the moment arm here is 0. Okay, so by multiplied by 0 is going to be 0. Looking at this equation, dy multiplied by 16 minus 48 multiplied by 8 plus 8 multiplied by 4 equals to 0, I'm seeing only one unknown, which is dy. So I can simply solve for dy to be 22 kips. Now I have one of the unknowns. Remember, in this equation, equation number 1, I had 2 unknowns. Now, if I introduce the 22 right here, I can solve by substituting into equation 1. I can solve for by. So by plus 22, the one I got from the summation of the moments, equals 8 plus 48. I will end up having by to be 34 kips. Now we're ready to answer the question. Write the equations for the shear and moment for the beam using an origin at end A. So this is what we have so far. Okay, I need to write 2 equations for the shear. The first equation should be in the segment between 0 and 4, and the second is going to be in the segment between 4 and, not 16, the end of the beam, x equals 20, which is 4 plus 16. So I have 2 equations. The first one is going to be for x between 0 and 4, and the other one is going to be for x between 4 and 20. Let's take this segment. This segment here, if I make a cut, I will see a shear force, Vx, and a moment, Mx. Okay, how do we get the value for these? Because if I get the values or the equation for these are the equations for the shear and moments I'm looking for. Basically, do the summation of the forces and summation of the moments. Let's do the summation of the forces in the x direction and the y direction first. So if I want to make the summation of the force in the y, how many forces do I have in the y? I have the 8 pointing downwards and the Vx pointing downwards. So minus 8 minus Vx will equal to 0. How many unknowns? 1. So I can simply say that Vx equals minus 8k, which means that in the segment between x equals 0 to x equals 4, I have a constant shear. Remember this until we draw the shear and bending moment diagrams. We may verify that. Now the other thing I'm after is the mx, taking the summation of the moments about point x, which is this point right here. How do we do this? First we have to put mx, which is a moment at point x, plus, now I'm taking moments about this point, so that means this Vx, which passes through this point, will not come into play. The only force I have to consider that will create a moment at this point is the 8 kips. So what is the moment by this 8 kips? It's 8 multiplied by the distance x. Okay, so it's 8x. What is the direction? or is it positive or is it negative, I will see that it will rotate counterclockwise, which is the same as my assumption, so it will be a positive 8x. And I will set this equals to 0 again. Now what will I have here? I can solve for mx to be minus 8x. Okay, for this segment I got the equations. Vx is minus 8k, and for mx I have minus 8x. Now let's look at the segment between 4 and 20 feet. Now this is the segment I should study. That's the one I'm talking about. Okay, this is a tricky one. Just try to be with me. The distance x is measured from this point all the way to this point where you make the cut. Now, if this distance is x and this distance is 4, what is the remaining distance? It's x minus 4. Now, what do we have? We have to concentrate this distributed load. Remember, I'm taking moments and I'm taking what? You guessed it, shear force. So this is the shear at the cut. Again, I'll call it Vx, and the moment I'm gonna call it Mx. Now we are ready to go ahead and apply the equilibrium equations. I'm gonna use two equations, which are the summation of the forces in the y direction. That will help me solve for Vx, or get me the equation actually for Vx. And if I do the summation of the moments about this point, the point I made the cut at, I will get the equation for mx. So let's go ahead. Summation of the forces in the y direction should equal to 0. What do we have? Minus 8 plus 34 minus this force. I know it's not a number. It has a variable x in it, but it's minus this. Minus Vx should equal to 0. Now I can just simply say that Vx equals to minus 3x plus 38. That's basically the equation for the shear force between 4 and 20 feet. Another way, if you want to find the shear force, the value for the shear force at any point between B and D, just at what x are we talking about? Let's say it's somewhere in here. Let's say it's in the middle of 16. So your x will be 4 plus half of 16, which is 8. That gives me 12. So if I plug in 12 in here, I'll get a value for the shear. Now, this is the equation, the final equation for the moment. But this is how we get it. The summation of the moments should be equal to 0. Let's go through the equation one by one. So we have mx, and remember, I'm rotating about this point, so it's a good practice to start away from this point and going toward the point of rotation. But first you have to include the mx. So mx, then 8 multiplied by the whole distance. The whole distance is x, and it's counterclockwise, so it's positive. Now I have the 34 multiplied by this distance, which is x minus 4, but it's a negative. Why is it a negative? Because it's rotating clockwise. So 8 times x, 34 times x minus 4. Now I have this force, which is the 3 times x minus 4, and it's rotating counterclockwise. And what about the distance? It's the distance between the point of action to the rotation. It's half the distance of x minus 4, so it's basically x minus 4 over 2. Now this is the force and this is the distance. If we simplify this, we will get mx equals to negative 1.5 x squared plus 38x minus 160. Now we'll try to use the equations to evaluate the moment at section C. Remember, section C is 5 feet away from D. So, or 5 feet away, I'm sorry, 5 feet away from support B. So this is what we do. We will use the equation for the moment. Since C is in between B and D, so we will use the second moment equation we got, not the first one. Remember, point C is located in the second segment, which is between 4 and 20. So we'll use mx equals minus 1.5 x squared plus 38x minus 160. Set x equals to 9 feet. Why 9? Remember that C is 5 feet to the right of B, and the origin is 4 feet to the left of B. 4 plus 5 is 9 feet. So MC equals 1.5 times 9 squared plus 38 times 9 minus 160. So MC will get 60.5 kip foot. Now we'll try to locate the point of zero shear between B and D. Remember, between B and D, we are talking about the shear equation between 4 and 20 feet. That's the second shear equation we got. So we will use this equation, which is the second equation we got. Now we need the zero shear. That means we need to substitute a 0 for Vx. So we set Vx to equals to 0, and if we solve for x, we will get 12.66 feet. So starting from point A, if we move 12.66 feet, the value of the shear will be 0. Now, locate the point of zero moment between B and D. It's a good one. Okay, so we will use, again, B and D. We will use the second moment equation. That's the one. Now, set mx equals to 0. So it's a quadratic equation. We'll have two x's, or two zeros. The first 0 is at x equals 5.33, and the second x is going to be at 20 feet. I want you guys to remember these values. Write them down on a piece of paper, try to memorize them, I don't care. But remember, x equals 5.33 and x equals 20 feet. At these 2 points, we will have 0 moments. Now, evaluate the maximum moment between points B and D. So, what's the maximum moment? Think about it. Remember the maximum. Remember this. It's a very good piece of information. The maximum moment is located where the shear is 0. And in question C, we found out that. Let me go back a little so you know. Here we are. Locate the point of 0 shear. We found that x equals 12.66. At this distance, we will have 0 shear. So if we will have 0 shear, that means we'll have a maximum moment. So the maximum moment is when the shear value is 0. That is when x equals 1.66. So we'll use this equation again, and we'll set x equals 12.66. We do this, we'll get 80.76 kip foot. Now, we'll try to draw the shear and bending moment diagrams. We have, this is the shear force, 8. Then between here and here, we don't have any forces, so the shear diagram will move horizontally until we reach the reaction here, B, at point B, which was about, I can't remember, it's probably 34. So we jump 34 units upwards. So what's the value here? it's 26. Now remember, at the end we need a shear force equals to the reaction, which is 22. But I have this distributed load. What is it doing? Basically what it does, it takes you down 3 kips every foot. So you are at 26. And if you move 1 foot away from this point, you will be at 26 minus 3, which is 23. If you move 2 feet, you will be at 26 minus 3 and another 3, that's 20. Basically, you'll be going downwards like this. So we have a point here where it crosses, but we know that points, how far is it from B or how far is it from A. But at the end here, we have a reaction that will push us upward. Yeah, here's the point. It's 8.66 feet from here, and if you add 4 to it, it's going to be 12.66 feet. Again, back to this reaction. The shear force diagram will close, and the value here is 22. Now I'm interested in the bending moment diagram. Again, that's the beam. How do we start? Okay, the value at the cantilever end here is 0. At any cantilever end, the moment is 0. And at this point, right here, what is the value here? I mean, we could have done this this drawing directly by finding the reaction without going through the equations, but I want to verify that my equations are correct. Okay, so if I want to know the value of this moment, I'll go up to the shear diagram and calculate the area below the shear diagram from the beginning of the beam until the point I'm interested in. So it's 8 times 4, which is 32. Now I want the value of the moment here at this point where it intersects. Remember, it's the maximum moment. The moment diagram should look like this, and the value we got this one before, 80.67. If you want to know how to get the shape of the moment diagram, again, up to this point, calculate the area below the shear diagram. So the area here is minus 32 because it's 8 in the negative direction multiplied by 4, and the area here is the area of this triangle, which is 1/2 multiplied by 26 and multiplied by 8.66. Now the area here is positive and the area here is negative, and if you add them together you'll get 80.67. Remember when I asked you to memorize the 5.33 and the 20? These are the 2 points where the moment diagram has a 0 value. This point is 5.33 away from A. 4, 1.33, so the moment diagram crosses this right here, and at 20, which is at the end of the beam, we have a moment value of 0. So that's it. That's how we do it. I hope that's helpful. If you have any questions, just send me an email or comment on this video. Thank you.